Hello, Chemistry 11. This is Mr. Chan. And remember last day, hopefully, what happened was we talked about the difference between molecular and covalent solutions and about ionic solutions and how they both dissolve in water, but one dissociates or breaks apart completely into its component ions, while another just changes phases from solid to aqueous. Now, recall this breaking apart into its component ions is called dissociation, and is represented by this equation called the dissociation equation. Please remember, dissociation and decomposition are not the same. One is breaking apart an ionic solid into its component ions in solution, while the other one is breaking apart the ionic solid into its component neutral elements. Then we went over how we can apply the dissociation equation to find, let's say, the concentration of ions. And we went back over molarity, something that you should have learned from Chemistry 11's mole unit. Now, what we're going to do today is we're going to talk about another concept in solution chemistry, talking about dilutions. Now, when we talk about dilutions, it is when one either adds water to a stock solution or mixes two solutions together. Now, the key thing is, you might say, well, what is a stock solution? When you think about a stock solution, it's a high concentration solution. You've used this in your everyday life, like say chicken stock. If you're making soup, you need to add chicken stock, and that's a high concentration of chicken flavoring. So when we talk about stock solution in chemistry, it's a high concentration solution. Now, when we talk about dilution, it's used to determine the final concentration of a substance after it is mixed with another liquid. So what you want to do is you want to find the final concentration or the resultant concentration after you mix. Now, one thing is key here. In dilution, the number of moles of solute is always constant, or the number of moles is always constant. Only the molarity and the volume change. If the number of moles is constant pre and post dilutions, then we can have the following. The initial number of moles is molarity times volume. And that comes back to the little triangle that we used up here. And the final number of moles is also molarity times volume. Now, therefore, since the moles do not change in dilutions, or the initial number of moles is equal to the final number of moles, then we have this idea of initial molarity, so MIVI, the initial volume, should equal the final molarity times the final volume. Now, this particular concept is key in terms of solution chemistry. This idea that you have a constant number of moles. And the equation that you should focus on is this one here. Okay? This one is key. Now, some of you might say, well, I don't get it. Well, what I'm going to do is I'm going to show you a particular diagram, okay, particular simulation. So let's say we have here. So what we have is we have a drink mix. We have a certain volume of water. So let's say I add some drink mix. Okay. Now, notice we have a specific volume on the left-hand side. We have a specific concentration. Now, let's say if I add water. Notice my volume has increased, but notice the concentration has decreased. Conversely, if I reduce the amount of water, look what happens to the concentration. So if I were to evaporate the water or reduce the volume, notice I have a lower volume, but a higher concentration. So there's an inverse relationship between concentration and volume. If one goes up, like what I'm doing with adding water, the other goes down. Notice I never added any more drink mix. So that's what I mean when the number of moles is constant before and after dilution. That's what I said here. Okay. Now, so what I want to do is I want to go over a couple of questions for you just to make life, just to hopefully see how things work. So what I'm going to do is I'm going to go over the concentration and dilution calculation worksheet. And what I want to do is I want to go over question number, let's say question number 6B. And later on, I want to go over question number 9B. Okay. Now, question number 6B is pretty straightforward. It says, what is the molarity of a solution prepared by diluting 25 mils of 0.4 molarity potassium hydroxide to each of the following volumes? Now, the key word here is you see the word diluting. Okay. Now, sometimes I will use the word diluting, sometimes I will use the word mixing. But in this case, what you're doing is you're starting off with one solution and you're changing the volume. Okay. Now, in this scenario, by reading the question, you are able to say, hey, I'm going to be using dilution. I'm going to be using that MIVI equals MFVF. So in this case, if we were to take a look at question number 6B, so what we do is we go MIVI is equal to MFVF. And if we look at our values here, so let me get that solution out. So I start off with 25 mils of 0.4 molarity, and I end off with 83 mils. So what I do is I do 0.4 molarity times 25 mils is equal to final molarity times 83 mils. Okay, and you solve for final molarity is 0.4 times 25 mils all over 83 mils. And I get my answer. So in this case, 0.4 times 25 divided by 83. And I get an answer of 0.024 molarity. Now, you might say, well, Mr. Chan, I don't get it. You know, do we need to change to liters? And the answer is no. The reason being is because in this particular case, the milliliters cancel out. And so it's just, you can keep the same units in milliliters. Now, if you're saying, hey, I want to change it to liters, by all means, not a problem. All right. Now, the next question I wanted to talk about was question number 9B. Now, 9B is actually a little bit trickier. And in terms of the concept and the question and how it's approaching it. So in this particular case, it says, in each of the following silver nitrate solutions, how many milliliters of water should be added? Now, the key word here is should be added. Okay, to obtain a solution that has a concentration of 0.1 molarity. Now, when you take a look at this, you still start off with the MIVI equals MFVF, because what you're doing is you're starting off with a solution and you are adding water. You're adding water to it. So in this particular case, what you would have is we start the same. So I'm just going to do it in a different color. So we have MIVI equals MF/VF. And what we could do is initial volume and molarity would be 0.250. Volume would be 20 mils is equal to MF and V. Oopsie, I know my final molarity, which is 0.100 molarity. And you have VF. Okay, now that's pretty much the same setup as what we had done before. Now, so what we do is we divide both sides by 0.100, divide both sides by 0.100, and I get VF is equal to 0.25 times 20 divided by 0.1. So I get 50 mils. Now, but if you look at the question, if you look at the answer here, 9B, the answer was 30 mils. And the key thing is this, why is it 30 mils? Is because of the question is how many milliliters of water should be added. So when you did your solution, when you did your question, this 50 mils is basically the entire final solution. So to find out the amount of water, so if we were to do the amount H2O added, so what we would do is we would take 50 mils minus the original 20 mils, and that would give me 30 mils. Okay. Now, this is where you have to be able to read the question and sort of deduce what they're asking for. Because if you take a look at, let's say, question number 10, it says, what will be the final concentration of each of the following solutions if the volume of the solution is increased by 20 mils by adding water? So what does it mean when it says the solution is increased by 20 mils? So that is something that you have to sort of be careful of. It's not always that straightforward as in question numbers, let's say 6, 7, and 8. But you might have to sort of look into the questions a little bit more. All right. Now, so what I'm going to do in the second part of this video is I want to go over, combine what you learned here about dissociation equations and this idea of dilutions where we have the M1 V1 is equal to MF VF. And what I want to do is I want to combine it together. Because in this particular scenario, in this questions up here, I added water. So the next level of question would be dissociation and dilutions. This occurs when one mixes two solutions. One needs to consider the concentration of ions when doing the dilution calculations. So the question would be, example would be, what is the final concentration of ions when you mix 425 mils of 0.842 molarity aluminum nitrate and 318 mils of 0.525 molarity Ki. Now, again, the key word here is mix. Okay, so again, because you are mixing, what you want to do is you want to do dilutions. So the first step is you want to do dilutions for each solution, for each substance. What do I mean by this? Okay, let me just draw a nice little line here. So let's say we have our aluminum nitrate. So what we do is we do the M1 V1 is equal to MF VF, just like what you did. Okay. And in this case, the initial molarity is 0.842. The initial volume would be 425. The final molarity you don't know. Final volume is 743. You do the same thing for Ki. I'm going to do it in a different color. So Ki, you still have MIVI is equal to MFVF. So again, what you have is 0.525. Volume is 318 is equal to MF and 743. Now, notice the final volume is 743 because you're mixing two solutions. You should get the same final volume. And again, what you would do here is you divide both sides by 743. And on the Ki, you also divide by 743. Here, 743. And what you get here for aluminum nitrate, your final molarity would be, let's see, 0.842 times 425 divided by 743. So I get 0.482 molarity. And for Ki, you get your final molarity would be 0.525 times 318 divided by 743. You would get 0.225. Now, remember, what is the question asking for? You're looking for the final concentration of ions. Now, both aluminum nitrate and potassium iodide are both ionic, so they both break apart into their component ions. And this goes back to the dissociation equation, breaking apart into its component positive and negative ion. So if we do that, so in this particular case, you have your aluminum nitrate. Let's see, let me just redo this. You have your aluminum nitrate, breaks apart to aluminum plus 3 and 3 nitrates. And you have your Ki breaks apart to K plus and I minus 1. So if we were to do the concentrations here, this would be 0.482 molarity, 0.482. This would be 3 times. So 0.482 times 3. This would be 1.45 molarity. For the Ki, it's fairly straightforward. So this one would be, if this is 0.225, this would be 0.225. This would be 0.225. Okay. So what we did was we just combined, let me just see if I can move that here. There you go. What we did was we just combined the two concepts that we taught today and last day, where you had to do the dilutions, okay, and you use the idea of MIVI is equal to MFVF, and then you applied the new concentrations into the dissociation equation. All right, folks, that is it. Thank you very much. Have a good day. Bye-bye.